from a company called PLX came to me and he said, Jose, I heard you're looking for people bringing optics to harsh environments. And I said, yes, that's something that I'm really looking at. So Itai came from New York, and he's going to talk to us about the technology that they use to have optical instruments in harsh environments from space to automotive. Thank you very much for coming all the way from the US. The floor and my friendship now is yours. Thank you.
Well, thank you, Jose, for inviting me over. Thank you, Carlos, for being so kind to us. For us, it's the first time being at EPIC, and I must commend both Carlos and Jose for creating such an energetic environment. I mean, all of you are just wonderful people, and got the chance to speak with some of you. Itai Vishnia from PLX. We are from Long Island, New York. PLX had started as a fabrication of essentially conventional optics. In the early 70s, PLX developed a method to manufacture domes. This was, at the time, MRF was not in existence, so that would have been taking anywhere between 3 months to 12 months. That machine, we called the machine as a scooping machine. Today, I think you can practically scoop some ice cream with it. MRF is doing a great job. With the next generation, we've been focusing on predominantly new technologies and investment in R&D. I think that the picture here at the front, and I do have this laser, hopefully you'll be able to see it, speaks for itself. Our optics, which you can see here, it's both in aerospace, military, and commercial applications. That was the slide I was talking about before. Our corporate circle is supported by Total Quality Management. We are ISO 9001, 2015. We are vertically integrated. We have the entire manufacturing team in-house. We have the standard conventional fabrication of a machine shop, glass machine shop, precision optical shop, various assembly labs, including class 100 for both aerospace, semiconductor industry. Summarizing a technology in 5 minutes is almost impossible, so I decided to just bring a short demonstration. The original one has some sound, but I'll be in the background. So what you see here is essentially a conventional optical setup for demonstration purposes. For the ones in the spectroscopy industry, you might recognize this structure. Short discussion with Simon from Trump made me realize that I probably need to emphasize the word monolithic. We obviously see an assembly that is comprised of multiple parts, so why monolithic? So the monolithic aspect is essentially interpreted after the assembly. It becomes completely inseparable. As long as we give respect to the materials we work with and our process, which is very, very mature. We're talking about heritage of 20 years with multiple other technologies that were developed in between. Purposely didn't talk much about this because I thought that this would kind of give you an idea of what can be done. This was just an example of a Michelson or steel interferometer. We incorporated a retroreflector which makes this entire assembly invariant, but that particular, which I call it a sandwich-like structure, can be made from different materials as long as you match the CTE with the materials and incorporate our process. It becomes a rugged and stable design and would withstand all of the harsh environment you have in a combatant field and in space, including launch conditions. This technology essentially is comprised of monolithic structures, invariant optics, with the usage of hollow retroreflector and light optics as needed, specifically if we want to integrate systems that goes to a space or any military vehicle. Kind of wanted to just briefly talk about invariant optics. A retroreflector by nature is an invariant. For some of you that don't know what is a retroreflector essentially is a device that would return the beam back to its source regardless of the physical orientation of the device. Look at it almost as an invariant flat mirror. You look at yourself in the mirror, you obviously see yourself, but then when the mirror is tilted, you see your image wandering all around. With this particular retroreflector, the image will stay fixed. So that becomes very significant in a lot of aerospace applications, military applications, specifically if you want to transfer a beam around 100 miles. So LiDAR will be one of the applications. So this particular mirror represents a segment of a lateral transfer hollow retroreflector, and this is the second segment. And this would be just the optical path within the LTHR. Various applications, the various platforms that we are currently in, military, aerospace, and commercial, multiple applications, spectroscopy, interferometry, one of the older applications that we've been using this particular technology, laser trackers, we make the targets for the laser trackers, so essentially it's the ball. There is a retroreflector mounted inside the ball. Free space optics and LiDAR are definitely the most emerging industries which we are luckily involved. And that is where that particular most assembly that you've seen can be made from anywhere between 0.5 meter in terms of size all the way down to 3 millimeters, and yet comprised several optical elements, and it doesn't have to be just plano, it can be gratings, it can be even lenses. Any optical system that you have, if you're looking to get it into production or into an environment that is hostile at times or a bit rough, you can use that. I'm just going to go through several slides quickly without talking too much about the substance, but the test spectrometer actually benefited from our assemblies, monolithic assemblies, tropospheric emission spectrometers. This mission was actually in 14 years, so talking about heritage of our optics, this is as long as it can operate. It stopped operating only because the program stopped getting data, and they are ready to send the next generation. We make our assemblies from different materials. This particular one is beryllium. This is a back-to-back retroreflectors with high accuracy between the apices. This is the entire interferometer. In the alignment telescope of the Atlas program, we've made several assemblies. Actually, we created a whole module, which I'll show you quickly. I mean, there is sound here. I don't know if you have it on right now, but I'll just show you the first portion. The gentleman that speaks right now is from NASA, and he actually talks about the telescope alignment. This particular module is the one that we made, and it actually takes care of the alignment of three elements. It's the telescope itself that you see right now, made out of beryllium, and the laser itself that goes to Earth, and the laser tracker, which is right behind the LTHR. So you have an assembly that is comprised of two LTHRs, which are essentially a segment of a retroreflector. This particular program is interesting because it's related to, essentially it's a LiDAR version related to measuring the ice sheets in Earth. The ISAT-2, which is the program, is measuring the distance, essentially, by measuring the time, and getting a whole topography of Earth with a resolution of 1 inch, as opposed to the ISAT-1, which was 12-inch. Various programs that we participated in. The military aspect is very significant, specifically because of the combatant field. This is the boresight module. It's very similar to the telescope alignment. This is an FTIR spectrometer. You can see here the monolithic optical structure technology. The great advantage of that is that once it's being assembled together, it's already pre-aligned, it's rugged, it's need to be introduced to the optical path without any additional adjustment. We have the usage of a retroreflector that becomes a complete invariant unit. This is just to kind of give you an idea of what we've done in the past. We are looking for challenges, half-arc-second accuracies in that particular environment, different dimensions, all the way down to 2 millimeters and up to half a meter, and a sample of the environmental conditions that we're supposed to meet. Just a mosaic of some of the assemblies that we've made. This is actually a light-weighted, large retroreflector. It was 25 centimeters in size. The integration of the boresight module is here. And boresight, for some of you who don't know, it's essentially the art of aligning multiple axes. This is just an example of a LiDAR system. We have a conventional LiDAR system taking it into this, and free space optics, which is involving MEMS. It's a retroreflector that is assembled from silicon wafers. And thank you so much.
Thank you very much, Itai. Thank you.